objectives for this class are to discuss the components of a dataset, which are individuals and variables, and to explain the differences between different types of variables. Another objective is to describe several methods to graphically summarize the data for each type of variable. In any research project, after selecting the sample and choosing a data collection method, we proceed with the data collection process. And what we obtain is a collection or a body of information about the group of individuals in the sample. We usually call this a data set. Each data set includes a set of individuals along with the information collected about each individual. We can collect information about a variety of entities, humans, animals, objects, and so on. In social sciences, however, we most often collect information about human beings, so we call them individuals. However, you may hear statisticians and researchers using the term observations instead of individuals. Each entity, along with the information that we collect about it, is considered an observation. Each piece of information that we collect is called a variable. For example, age, height, weight, and so on. We call it a variable because although we collect the same type of information from every individual, the values recorded will most likely vary from one individual to another. Most datasets list individuals on rows and variables in columns. These can be reversed, but this is the most common format. Let's pretend that we collected some information about a group of participants in a trivia contest. We can see the name of each individual listed in a separate row, and the variables, or the information that we collected about them, in separate columns. So for each participant, we recorded the age, gender, the actual score on the contest, and the rank earned based on the score. As illustrated in the previous example, variables can be of different types. Some variables are called quantitative because they can take numerical values and can be used for computations, like test scores, for instance. Quantitative variables can be of different kinds though. Some of them are called discrete because they can only take specific values or rounded values like integers. A discrete variable is a quantitative variable that has a finite number of possible values or a countable number of values. An example of a discrete quantitative variable is IQ scores. They range from 0 to say 150 and can only be integers. A continuous variable is a quantitative variable that has an infinite number of possible values between integers. Such variables are weight, height, speed, etc. They can have an infinite number of decimals. Continuous variables can be divided into another two categories: interval variables and ratio variables. When variables are on a ratio scale, the value 0 represents nothing or the absolute absence of an entity. For instance, an object of height 0 or weight 0 doesn't even exist. For variables that are measured on an interval scale, the value 0 is simply the beginning of an interval and does not indicate the absence of that entity. For instance, the temperature 0 is simply a point from which we begin the scale, but there are temperatures that are at or below the 0 point, regardless of what temperature scale we use. Another type of variable is the categorical type. These variables are also called nominal and have a certain number of categories, but the categories cannot be ranked or ordered in any way. For instance, gender is such a variable, or the individual's names. These do not have a numerical value and cannot be used in computations. However, just for practical reasons, when entering data in the computer, the different categories sometimes receive a numerical code, like 0 for females and 1 for males, but these codes do not really have a numerical meaning. They're just replacing the words to ease the manipulation of the data set. Ordinal variables are similar to categorical variables because they also have a certain number of categories, but there is an important distinction between them. The categories here can be ranked. They have an intrinsic order. For instance, a test may have only two outcomes, pass or fail. Pass is definitely superior to fail. So even though we have only two categories, these two categories can be ranked. A similar example can be the SES status of the individuals in the sample. Another example are survey responses. When responses to survey items are provided on a Likert scale, we can have, for instance, four categories: strongly agree, disagree, and strongly disagree. These categories can definitely be ordered or numbered from 1 to 4 based on the respondent's degree of agreement. After we collect the data and we enter each variable in the dataset, the next step is to analyze the data. Before conducting more complex statistical analysis, we typically employ what is called descriptive analysis. This is an exploratory phase when we try to summarize the data using graphs as well as numbers, but we will just focus on the graphical representations. Our goal when using graphs is to illustrate the distribution of each variable, which means that we want to show the values that the variable takes across the individuals in the sample. We want to see what is the range of values and what values or categories occur more often than others. Now, the type of graphical illustration that we should use depends on the type of variable that we're working with. For categorical variables, we can use pie charts or bar graphs, whereas for quantitative variables, we use different kinds of graphs, such as histograms or plots. A pie chart shows the distribution of a categorical variable. It illustrates all the categories and gives the count or the percentage of individuals who fall into each category. This example illustrates the racial distribution of the student body at the University of West Georgia. This is real data, and each slice of the pie indicates the percentage that corresponds to each racial group. Pie charts are appropriate to be used only when all the categories put together form a whole, so all the percentages add up to 100%. Therefore, each individual can only belong to one category. Bar graphs are also used with categorical data, but the different categories do not necessarily form a whole, and individuals may be included in more than one category. For instance, this bar chart shows how teachers responded to the question, "What can be done to improve instruction in our school?" This is a type of question where respondents can check all the responses that apply. So some teachers may have checked more than one box. Therefore, the percentages represented by each column do not add up to 100%. Actually, in this case, I think they add up to 152%, but adding them doesn't really make any sense. The distribution of a quantitative variable tells us what values the variable takes and how often it takes those values. This is an example of a histogram, and it illustrates the distribution of students' weight. The first step in producing a histogram is to divide the range of possible values into equal intervals. Statistical software does this automatically, but you can change these intervals if you want. In this case, the values for the weight variable range between 100 and 280, and the intervals are set at 20 pounds. So in the first column, we see the number of students who have between 100 and 120 pounds. The second column represents the number of students who weigh between 120 and 140 pounds, and so on. When interpreting a histogram and any other graph, we try to describe the overall pattern and also to identify any striking deviations from that pattern. For instance, here we see that the majority of students weigh between 100 and 220 pounds. The distribution across the different categories in this range is approximately uniform except for the 120-140 category and the 180-200 category, so these are much more frequent among the students in the sample. We also notice that we have an outlier, one individual who is located in the 260-280 category. An outlier is an individual who falls outside of the overall patterns or records extreme values. Stem plots are also considered graphical representations, but they use numbers to show how variables are distributed. A stem plot looks like a histogram that is turned on end. This example shows a distribution of student IQs. The first column, labeled STEM, shows the first 1 or 2 digits of the IQ score, the tens digit and the 100 digit. And columns labeled leaves include the last digit or the ones of the IQ scores. For instance, in the first row, we have a stem of 3, which represents the tens digit, and a leaf of 8, which represents the ones. Together, they make an IQ of 38. In the third row, we have a stem of 5 and 2 leaves, 1 and 3. This means that one student had IQ of 51 and another student has an IQ score of 53. For each stem, the number of leaves show the number of students who have scores at that level. So we only have one student at the 30 level, 1 in the 40 level, 2 at the 50 level, 3 at the 60 level, 5 at the 70 level, and so on. We can tell from this graph that most students have the IQ at the 100 level. The IQ average in the population is 100, so it makes sense to have most of the students located somewhere around this value. Values that are very low or very high are less frequent. We only have 2 scores at the 130 level, 132 and 135, and we have an outlier with a very high score of 152. So to create a stem plot for each observation, you must first separate the first part of the number or the stem from the last part of the number or the leaf. Then group observations that have the same stem and write each stem in a vertical column, just like we've seen before. For each stem, you then write the leaves from every observation that begins with the same stem. Both the stems and the leaves should be ordered from the smallest to the greatest value. The population distribution of IQ scores has symmetry, which means that the majority of people are located around the average of 100, and the frequency of individuals decreases more and more as the IQ scores depart from the average. The curves that you see here are abstractions. Real data are represented using histograms. Curves are simply abstractions or a symbolic way to show the distribution of the data. The example on the bottom left side of the screen illustrates a symmetric distribution, or what we call a normal distribution, like the IQ scores, where the majority of individuals are located in the middle and the two tails have a similar length and height. The second curve is what we call a negatively skewed distribution, or a left skewed distribution. Here, the majority of individuals are located towards the higher end of the range of values, and there are only a few individuals towards the lower end of the scale. For instance, this could be a representation of graduate students' GPA. The majority of the graduate students in the education realm, for instance, have very high grades, and only a few have low GPAs. The curve on the bottom right corner of the screen represents a positively skewed or a right skewed distribution. Here, most individuals have lower values on this variable, and only a few have higher scores. An example of this type of distribution is the distribution of income in the population. Most people make under $40,000 a year, but some make quite a bit more, with a small number of people making many millions per year. A time plot is a graphical representation of how a variable changes over time. In this case, we collect data several times, not just once, and we record the values of the same variable at different points in time. For instance, this graph represents the changes in college tuition across years for public and private universities. Time is always represented on the x-axis, which is the horizontal axis, and y, or the vertical axis, represents the values that the variable takes over time. Data points are connected with a line to better illustrate the trends over time. In this case, we can see that tuition has increased over time for both public and private schools, but the rate of increase is much higher for private schools after the 1980s. In this presentation, we described the components of a data set and made a distinction between individuals and variables. We have also discussed the different types of variables and different ways to graphically represent the distribution of each type of variable. I hope that the information was clearly explained and that the examples provided helped you understand the material better.